Okay, as promised in the last video, we're going to actually learn how to plot points. Okay, so I want to plot the point whose coordinates are 1, 2, 3. So I'm going to start by drawing in my axes. So there's the x, the y, and the z axis. You'll notice all of the coordinates happen to be positive, so I'm going to just put some tick marks on the axes. I'm just only going to bother to do that on the positive axes. I could certainly do it on the negative axes too, I just don't need that. Okay. So to get to this point, if I were to start at the origin, which would be 0, 0, 0, I would come 1 forward, and then I need to go 2 to the right and 3 up. Now, it's easy to make a mistake here. If I go 2 to the right, a lot of people wanted me to come right over to here so that I'm lined up with that second tick mark. But if I do that, notice that the distance that I've traveled is that much, but that's a distance of 2. So I want to travel a distance of 2 from that point. Now you'll notice if I then connect this and complete a parallelogram here, that's part of this line right here, which would be parallel to this line. Here we've got y is 0, this is y is 2. The line where y equals 2 on the xy plane, because I haven't added any height to it yet, okay, is not straight up and down, it's parallel to the x-axis. Okay. So this point right here would be the point 1, 2, 0. The z value is 0 because I haven't added the height yet. Now I want to go up 3. And again, that's not going to mean that I come up to here to line up with where z is equal to 3. That's going to mean I want to come a distance of 3 up from that point. So that right there would be my point P, whose coordinates are 1, 2, 3. Now, if I've drawn in these dotted lines to sort of show the path I followed to get from the origin to point P, then I can see that those are its coordinates. If I didn't draw those in, and if I just had the point P, without all of this extraneous stuff here to indicate how I got there, it would not be at all obvious that that point was 1, 2, 3. And that's because when we're graphing 3 space on a 2-dimensional whiteboard like this, there are infinitely many points that I would accurately plot at exactly that location, even though they're different points. For example, if I held x to be 0 and y to be maybe about 1.2 and z to be about 2.5, that's another path I could take to get, and I'd end up right there. Now in 3 space, those are obviously different points, but my representation of them on a 2-dimensional whiteboard would overlap. Okay. So I'm just going to give you a point to try. Let's try the point Q, -2, 1, -1. I want you to just pause the video, try to plot that point, and do indicate, using just dotted lines, the path that you take to get to that point so that it would be clear, even if you didn't label it, what the coordinates should be. Okay. Welcome back. So let's see. I'm going to draw in tick marks this time on the negative x-axis, positive y-axis, and negative z-axis. Okay. So I would be going back 2, so that's going to take me to here. Then I've got to go over 1, so that's going to be a distance of 1 to the right. That'll take me to about right here. So this point would be the point -2, 1, 0. And then from there, I've got to go down 1. So I'm going to come this distance down. And right there, that's my point Q. Okay. Now, that's actually below the XY plane, because this point right here is on the XY plane. It's a little bit misleading unless you have those lines actually drawn in so that you can say, oh, I went 2 back, I went 1 over, and then I went 1 down. Okay, excellent. What I'd like to do next is graph an equation. We're going to graph a very simple equation, but we're going to graph it 3 different times. We're going to graph x equals 2. And we're going to graph it once in 1 space, and then once in 2 space, and then once in 3 space. Okay. So, if we're working in the real numbers, we would have this number line. Okay. If here's 0, that would be 2. We would plot that point. Fascinating, interesting graph. Okay, now if we're in R2 and we want to graph x equals 2. Okay. Well, here's my x-axis. This point right here, where x equals 2 on the x-axis, is going to be part of that graph. So essentially, the x-axis in 2 space is just a copy of what I have on the real number line right here. And so I can take this graph, and it's going to be part of my graph in 2 space. But if the equation just says x equals 2, that doesn't put any restrictions on what y can be. So if x has to be 2, I can't go from here left or right, because that would be changing the x value. But y is free to be whatever I want it to be. So I'm going to get an entire line, and that would be the graph of x equals 2 in 2 space. Now, you already know that that's how you graph x equals 2 in 2 space. I haven't taught you anything new, but that notion that this puts some restrictions on x, but not y. So I can basically, once I've graphed what I would have just in 1 space, I can then translate that graph parallel to the y-axis, and that's going to give me my graph in 2 space. Okay. That process of translating actually has a fancier word. We call that extruding. So we extruded that point parallel to the y-axis. Okay. So now, if I want to graph this same equation in 3 space, here's x, y, and z. Okay. So here's x equals 2. This is the x-axis. That's basically going to give me a copy of this graph. Okay. All right. Now, this puts no restrictions on y, so I'm allowed to go left and right. I can't go forward and back at all, but I can go left and right as far as I want to. Now, I'm going to draw that, but just as a dotted line, and I'll explain why in a moment there. Okay. But basically, that's giving me a copy of this. Notice, it takes a little getting used to. What would be a vertical line in 2 space ends up looking like a horizontal line here, because the y-axis is in the same position that I'm used to seeing the x-axis in. Okay. Now, this equation, x equals 2, also puts no restrictions on my z values. So, I can take any point on this line, and I can extrude parallel to the z-axis. So I can translate this vertically up and down. Okay. Now, to show that, I'm going to just draw a dotted line through there. Okay. But basically what I'm getting then is a plane. It's just a plane that's 2 units in front of the YZ plane. The YZ plane would be where x is equal to 0, so that I haven't stepped in front of or behind the XZ plane. Okay. Now, the way we draw a plane is we're going to represent a plane always as a parallelogram. Notice, since this is basically parallel to the YZ plane, I'm going to draw these sides as 2 sides parallel to the y-axis and 2 sides parallel to the z-axis, so that this actually is just a rectangle. Okay. It's understood that these boundaries are artificial. A plane, of course, goes on forever and ever and ever and ever, so it doesn't have any boundaries. But that makes it very hard to draw. So, if we draw a rectangle, and sometimes our rectangles will look like parallelograms, because remember, in 3 space, right angles don't always look like right angles. When we draw a rectangle, very often that's going to be symbolic of something that's infinite. But that's the basic way of drawing a plane. So that would be the plane that we get. And the reason I drew these as dotted lines here is because they really aren't part of even the artificial boundary at all, but they help me to see that I've got this point right here. This is the only point where it's really obvious that the x value is 2, because I had these tick marks on the x-axis. I came 2 out to get that. Okay. All right, so there's our very first plane that we've graphed. Now, there are 3 planes that are actually very, very important for us, and these are called the coordinate planes. So we've got the xy plane, and the equation for that would be z equals 0. So that's basically going to be all of the points that are down here where we haven't gone up, so we haven't gone above the xy plane, and we haven't gone down, so we're not below it. Okay. Then we've got the yz plane. That has as its equation x equals 0. So that's basically all of the stuff that's here determined by the z-axis and the y-axis, where x is 0. So we haven't moved in front and we haven't moved behind it. And then we've got the xz plane. That would have as its equation y equals 0. So whatever variable doesn't show up in the name of the plane, that variable is fixed at 0. Much as in 2-space, the x-axis has as its equation y equals 0, and the y-axis has as its equation x equals 0. The xz plane, of course, is determined by the z-axis and the x-axis, so that would be this plane right here that would be coming straight towards you. Okay. All right, I'm going to stop this video here, but what I'd like you to do before you start the next video is just show me how you would draw these 3 coordinate planes. Remember, the rule is we represent a plane with a rectangle, but of course, since we're in 3-space, not all rectangles look like rectangles. They always look like parallelograms, but they don't always look like rectangles, because even though we are using right angles, in 3-space, not everything that's a right angle looks like a right angle. Okay, so try to illustrate for me these 3 coordinate planes, and that's where we'll pick up in the next video.